exposed minus the cases, and prevalence is given. Standard error is this calculation right here, 1 over A plus 1 over B square root. Okay, so there's A, there's B, and that's what standard error is. Type 1 is given at 0.05, critical value is 1.96. I can barely read that. And then the upper and lower logit came from this value right here. Okay, natural log p hat 1 minus p hat. And I think that what I did was I did this one's plus, one's minus, so that when it came down here to calculate the p, you didn't have all this junk in here. Okay, this was just one already calculated unit, or already calculated value, and then you do the upper and lower limit of p and the upper and lower limit of the relative risk. I hope that clarified it a little bit. Did it? Still didn't help. I can tell it's still a lost cause, judging by the expressions. Okay, what's the problem?
Honestly, I didn't look at it.
Yeah,
okay.
I need to do it. I'll tell you my problems.
Okay, okay. Did anybody look at it?
I just didn't like it. I tried. I attempted.
Okay,
So I mean, I attempted the problem.
I tried to look at it, or you tried to do it?
I tried to do the problem.
Okay, Jared.
So I had caps lock logging into my email.
The upper and lower logit. Okay.
What's the difference?
Plus and a minus.
Is that it?
Yeah. See, the upper and lower logit. This is the actual logit function, but this was what I called logit was actually this entire expression.
Oh.
And upper and lower, see, is d4 1 minus d4. That's p hat. Okay, so it's that unit. And then minus d12. The 1.96, which is z, times d9, which is a standard error. So it was this, the upper logit was plus, and the lower logit is minus. Does that help?
Yeah, I didn't realize the logit was both.
Yeah,
The standard error.
I still kind of messed it up. One of these days I'll get it right. But you can see what I was getting. This actually is the logit. And this is just the expression that includes the logit. And that's what that is. So what I'm going to do is just recalculate, rename that. And then you can get upper and lower relative risk. Okay. Likewise, for the person time calculations, this was a little bit more straightforward. That's the upper and lower incidence rate. This is the standard error here, and then this is A, which is the number of cases, the exposure, which is total for T, which I changed it to 1 year because there was nowhere in the problem that I specified 10 years. And where I got this, it was 10 years. I looked back at my reference. But I wrote my problem poorly in order to get that 10 years out of you. So I changed it to 1. It doesn't change the problem because I said this how many cases there are in a year. It doesn't change the problem. It changes the limit. The limit's a little bit. But this is not significantly elevated since our incidence rate, which is essentially the SMR, is 0.19 to 1.35. Okay. Savannah, what was it about these problems that was specifying?
Well, considering when I was attempting them, it was prior to your upload. It was more just reading through the actual questions and seeing just a bit of wording at some points, and then it was more just, I guess, practicing with the equations and knowing how to get certain steps from the actual exam equation sheet, because not all of it's always given there. Sometimes we have to interpret from previous bits.
Okay. Is this helpful? I suggest that you guys look over this at some point before the exam on the 8th.
Will do.
And then I'll talk about it some more during the review. Okay. So that is going back to the third topic. Now let's take a look at topic 4, error. Okay. Oh, and let's take a look at Sakamoto. First question. Following our associations that have been suggested, which may or may not be valid, assess the validity of the associations, consider identify the sources of error to justify your conclusion. Okay. Cigar smoking is positively associated with baldness. Okay. Second one is alcohol consumption is positively associated with lung cancer. Okay. We talked about the second one. The first one we didn't. The way I think about this is like this. Okay, the baldness cigar smoking. Okay, I'd say that's probably a spurious relationship. I doubt whether there's any direct connection biologically between the two.
What about chemo?
I'm sorry?
What if they get cancer and have chemo, they're bald?
But that's not cigar smoking. Okay, well then that's the confounder, okay? Right. That would be the confounder. But let's assume there's no chemotherapy, and that typically, who smokes cigars?
Old dudes.
That's right. Old males, okay? Who's more likely to suffer from baldness? Old dudes. Confounder. And so that would be a spurious relationship. Likewise, with lung cancer and alcohol consumption. Okay, because both of these are associated with each other. Likewise, both of these are associated with each other, but this is the spurious relationship. So smoking is the confounder in that relationship. Yes?
When we answer confounder questions, do you want them laid out like that?
It makes it a lot easier to think about it and for me to understand what you're talking about. So I think it helps us both to do that, yes. Is this, any questions on it, comments? Is this clear? Is it mystifying? Which is what, tell me, talk to me.
Makes sense to me.
It looks clear.
Okay, yes, Sam.
On the exam, if you ask us to find a confounder, can we just pick anything that we think is actually related to, or are you looking for a specific answer?
Well, for instance, let's say that I had asked this question on the exam, and you came up with chemotherapy. Okay, just as an example.
And that's wrong.
Now, the problem with it, okay, that's not completely out in left field, but there's a problem. Chemotherapy, yes, that's associated with baldness, but as far as I know, there's no association with cigar smoking. Okay, so that's what you have to think about. Is your confounder that you come up with positively associated with both of those things? Okay, does that make sense? Because that's what, and I can't think of another confounder here off the top of my head, but if you can come up with a good one, sure.
Servicemen,
Servicemen.
they take the haircut, they smoke, they're not bald. Some could go bald.
The old guys.
This is,
I know.
okay, this is not an acquired trait here. We're not Lamarckians, okay?
Can you show a negative association?
Yes. Yeah, that's negative confounding.
That way.
No. Because this is positive, this is positive. So this is the confounder that actually is the cause of baldness.
Can you give an example of a negative one?
Negative confounder.
Yeah.
Exercise and risk for heart attack. because exercise reduces your risk. It reduces the risk associated. High fiber diet and colon cancer can be another one. Think of things that you would get a protective effect from being exposed to. An odds ratio or a relative risk that's significantly less than 1.
So like steel toe boots and toe amputation.
Exactly. Exactly. Yeah. A good occupational example. Thank you. That makes sense.
Is the steel, if you press the steel, it can cut your toes off? Don't you watch Mythbusters?
Okay.
I stay away from it if you could.
Other questions or comments about the first one? All right. Now, let's talk about the second one. Children who ingest lead paint are at risk for lower IQ scores than children who do not ingest lead paint. Okay. And I got this one from when I did my MPH at Rutgers. And you know where that is? It's in northeastern New Jersey, just outside of New York City. So there's a lot of places there where there are very old rundown buildings. Okay? And they actually run into problems like this because lead apparently is sweet. So little kids will actually, and if it's peeling, they'll pull it off and eat it. Okay? So they said, is there a relationship? So they said, okay, children of lower socioeconomic status are higher risk for low IQ scores. Children of higher socioeconomic status. Children in higher socioeconomic categories ingest lead paint, their risk for reduced IQ is less than children of lower socioeconomic status. So what I want you to do is qualitatively describe this relationship. What is this that we're talking about here? We talked about bias, confounding, effect modification, and random variation. Yes, this is effect modification that I wanted you to qualitatively describe to me. Okay? And there's a number of different ways you can do this, but this is the way I chose to do it. And by the way, these are arbitrary values. Okay? Just arbitrary that I assigned just so that I could get a graph. So, one of the things that we talked about is that risk for lower IQ is greater if you have lower socioeconomic status than if you have higher socioeconomic status. That's probably related to access to education, environment, that sort of thing. Right? That's the most likely cause. And then we have the relationship between risk for low IQ with presence of lead paint, in other words, more likely to chew on it or eat bits of it or something like that, and the absence of lead paint. Okay? This is risk. So these are the kids that come in with low IQ scores, the ones that have high risk, right? So let's combine them. And there's two ways you can combine the two. The first one is to put lead paint ingestion qualitatively on the x-axis. You guys remember? This is an aside, but I can't resist. But there's an actual name for the x-axis and for the y-axis. Do you remember what it is by any chance? Did you ever hear it?
Independent?
I'm sorry?
The independent and dependent?
Actually, that's correct, but that's not what I had in mind. They're kind of obscure, but I just think it's cool. The x-axis is called the abscissa, and the y-axis is called the ordinate.
Oh, it sounds like a balloon question.
Yeah.
For,
that's why I tell you
During
these things.
graduation. Yes.
During graduation speeches.
Yeah.
Well, no, Drew,
Actually,
he has to defend
yes.
the G.
Because we used to do graduate research projects. Now we do graduate capstone projects. Graduate research projects had an actual presentation. And one of the students who was giving her presentation, guess who shows up to it after 5 minutes?
The wizard.
Dr. Bloom showed up to it after 5 minutes. And she's giving her presentation. And what I usually try to do, believe it or not, is to not give you too much jargon, just enough jargon in each of the disciplines to understand it. That's my objective is to just kind of tread the line between too much and too little. And, but he doesn't do that. Okay, so he raises his hand and he says, did you account for heteroscedasticity in your, in your research? And she stood up here, easily 2 seconds. And we said that, and I thought, oh God, I never mentioned that, because I talk about it all the time, but I never once gave it a name when I did quantitative methods. Did Dr. Gallimore talk about heteroscedasticity?
Like one 30-minute block, and then was done. And then
Okay.
we just kind of moved on, and he was there the whole time.
So he uses the word. Okay, that was my mistake. I shouldn't have used the word, but I talked about testing for it without ever actually naming it. Okay. So anyway, that's an aside. Let's get back there. So we have on the abscissa here the ingest lead or do not ingest lead, and then we have a socioeconomic status line. So the line for lower socioeconomic status shows that when lower socioeconomic status who don't have access to lead ingestion, say they have project housing or something that doesn't have lead paint in it versus the ones who do, you have a higher, this increased relationship. You also have an increased relationship among higher socioeconomic status kids. However, that is less pronounced, okay? Probably because of the presence of better resources, better educational resources. Even if they somehow get a hold of paint or lead or are exposed to it some way, they are less affected by it. So, when you have a relationship that looks like that, that is a, matter of fact, let me show it to you. I want to try to emphasize where these things are that I'm talking about. You guys remember?
I remember the multiplicative and the additive part.
They're at the bottom. They're right before we're having.
Yeah. So these are synergistic, and these probably are multiplicative rather than additive, right? Because the combined effect of exposure to lead paint and low socioeconomic status has a greater, causes greater risk than higher socioeconomic status and exposure to lead. And so this is a multiplicative synergistic type relationship, kind of like cigarette smoking and exposure to asbestos. Okay, the two together, as bad as either one is by itself, the two together are multiple times worse. Okay. You can also graph it in this direction. Okay, this is the low socioeconomic, high socioeconomic status. So rather than drawing your lines based on socioeconomic status, you draw your lines based on lead ingestion, and you get a similar relationship. Okay, for those who ingest lead, there's a greater risk than for those who do not ingest lead based on socioeconomic status. So that's a type of multiplicative synergistic effect modification. Does that make sense? Yes, no? Throw something at me? Yes, no.
Does it matter how steep our lines are in terms of drawing these graphs for, let's say, the exam? And then, would you want us to talk about heteroscedasticity in the exam?
Heteroscedasticity has nothing to do with this. It was just an aside story.
Isn't it the variability of the variables, essentially?
Heteroscedasticity has to do with how much your assumptions of independent and identically distributed error in linear models, like for analysis of variance and for regression and that sort of thing. So it really doesn't have too much to do with this. But like I said, that was just a story. I was trying to lighten things up a bit. I'm usually frustrated in that regard, so I don't know why I try.
It's appreciated, Max, don't worry.
A for effort.
Just keep track.
That's right, keep
The
trying.
max factor.
Okay. So what I would ask, let's talk about this. What I might ask you to do is give you a scenario like this, and then give me a hypothetical graph. I mean, you don't even have to come up with these bogus values that I did. The only reason I came up with those values is so that Excel would graph it. Okay, that's the only thing that's mean. Okay? You don't have to do that. You can just give me a qualitative graph and then describe it. Okay.
Can you give an example for us of a question that would have us draw an antagonistic or something?
Antagonistic, okay.
'Cause
Well,
that-
let me do the one that I talked about last week. Okay, with hip fracture. And I don't think I labeled it as such. Yeah, no, I didn't label it as such. But here we've got, let's see, I did male, female. Let's see if we can do an old, young. So here we do young in parentheses. And here we do old in parentheses. Right? And here we do risk. Okay, and that's our increasing risk. Okay. So let's see for, let's do a line for females. Okay. That's females, right? Let's do a line for males. Okay?
Why are we red? Just kidding.
Why are males?
How dare you assume your gender?
Yeah, Max.
Okay. Let's use some more neutral colors. How do you like?
It's an election
How do
year.
you like green and blue? Who wants to be green? Who wants to be blue?
Max, color Max.
What's that?
I abstain from
color.
voting.
Blue
Okay.
and pink, right?
Wait a minute. It's gotta be all.
Way to go, Mason.
There we go. All right. I did it the first time last time. Okay. That's it. That would be antagonistic. Okay.
Stop antagonizing.
Males perhaps might be greater risk takers as 17 or 18-year-olds. Therefore, more likely to fall and break something or hit, for example. However, they gain more judgment as we age and are less likely to fall and do something horrible to ourselves. Women have good judgment from the beginning, right? However, they also suffer from osteoporosis more so than men do. So they're more likely to break their hip or be at risk as they age. That's antagonistic. Does that make sense?
Yes.
Okay.
Yes.
And the colors are okay?
Yes.
Careful.
Yeah. Okay. All right. Did you guys enjoy Sakamoto's article? Et al.'s? Who read Sakamoto et al.? Thank you. Okay. So let's take a look at these guys. What my question was, read the article by Sakamoto et al. And discuss the steps taken by the Office of Control for Performance Behavior discussed in class. Okay, let's go take a look at Sakamoto. And you can tell that this was some kind of a grant. because everybody and their brother wanted to be on the grant. And so that's typical. And they were all on the Japanese Orthopedic Association. The things that they looked at and were interested in were, first of all, gender. So they wanted to make sure that they had, see what their gender and age distribution looked like. What I found interesting is how young some of the people were that they located in some of the facilities they went to. I mean, they had, and also how old some of them were. I mean, it ranged from 37 to in excess of 100. That's a pretty good age range there. And their distribution was substantially more women. Women usually outlive men, so there's substantially more women in the groups. They also were interested in what type of diseases they suffered from. Okay, all of their subjects wouldn't have been in the situation, the healthcare facilities they were in, if they didn't suffer from something. Most of them, cerebrovascular, like stroke and that sort of thing. But next to that was dementia. Okay, so that's why these people ended up where they were. Okay. So they made an attempt to at least describe the age and gender distribution, types of diseases they suffer from, and then they distributed them between the exercise and control group randomly, apparently, because they wanted to see whether or not, if they practiced every day between unipedal standing, in other words, balancing on one leg, they practiced that on a daily basis, whether it would reduce the falls. And even though you're really not supposed to do this, they make it very clear that they kept this off and started 116. Okay. So they try to make it real clear. I don't think it distorts the data, even though it's not the preferred way to display data. But they came up with what's an apparent significant reduction in their exercise group. Now the ones that did fall, there was no difference because it didn't reduce their likelihood of breaking a hip, but it did reduce their likelihood of falling, and therefore their as a secondary effect, reduced their likelihood of breaking a hip. So they did make an attempt to make sure that they had no bias in it by taking consideration into the demographics of the groups that they dealt with, apparently. What I'd like you guys to do is I'll talk about it again next week, and I'd like you all to take a look at the article and tell me what you think about this. Okay. We'll start out with a discussion next week again, but that was a summary of what they talked about. All right. We can move beyond error for the time being. Now let's look at the first exercise in analytical methods. Okay, let me open, because we will be talking about analytical methods more today, finishing it up. So, this is from a real study conducted in Sweden about exposure to EMF, and they did a matched case control study. Okay. What they were interested in is fields above, the first table is fields above and below 2 milligauss, and the table 2, they did fields above and below 3 milligauss, and they wanted to see what the risk for childhood tumors were. Okay. Now, this was an '86 study. Just so you know, doing a case control analysis like this probably would be much better, you get better results if you, instead of these dichotomous categories, here above and below 2 milligauss, here above and below 3 milligauss, whether you just measured the exposure and then kept it as a continuous variable in a regression of some kind. In this case, it would be a logistic regression, which we'll be talking about. That's our next topic after this. Because that's what you do with logistic regression. And then you can tell whether there's a significantly increased risk per milligauss exposure. But they chose not to do that in this study, and therefore that we have two separate, it's the same data because they had 180 pairs in both of these. They had 360 subjects in both of these. And so it's the same 360 subjects, they just divided them up differently. You get two different analyses. So what I wanted you to do was to do the matched case control analysis for both one and test, do the chi-squared and the confidence interval, and then do the transformation and go through the whole process again and tell me what, whether they were needed to be, whether they needed to be matched or not, whether there was confounders present. Okay. So for table 1, based on above or below 2 milligauss, the matched analysis looks like it's not significant. Chi-squared is 2.9, it's less than 3.84. The confidence interval contains 1. Not much, but it contains 1. So it looks like it's not significant. When we go ahead and do the transformed analysis, we end up with something very, very similar. The odds ratio, the upper and lower limit, and even the chi-squared value is very similar. Go on and do the same analysis for table 2 based on above or below 3 milligauss this time. And you get something that is very rare. You get a lower limit of 1. Okay, that's a call right there. When you transform it, you get slightly different results. Right? This shows to be not significant. This shows to be not significant. These are the results are very similar. They're slightly different, but 1 versus 0.9, 16.7 versus 19.8. That's pretty darn close. So, what I conclude from this is that not only is there, based on this, strictly speaking, not a significant relationship, but it looks like their matching variable wasn't a confounder, which even further implies that they could have subjected this to a logistic regression instead of putting it into 2x2 tables for analysis. Having said that, and that's strictly speaking, if you saw these results right here, even the ones on the previous page, if you saw these results, how would it affect your decision to buy a house that's under power lines? Now, strictly speaking, this isn't significant. But, and I'm just curious, I'm asking you how you would think about it.
Can I listen to the radio still or no?
I'm sorry?
I said, can I listen to the radio still or no? So the power lines.
Well, it depends whether it plays in your head without a set or not.
At face value, because of the odds ratio, that it went up from 2.4, 2.5 up to 4 with only one level of increase. But you have to get power somehow.
That's true. We have to get power somehow, but would you want a house that's under the power lines?
I mean, it's showing.
That's my question.
I know. I mean, it's concerning that with only one level of mg that you're going up, you're getting that much increase in your odds ratio. So,
Yeah.
at face value, no, even though it is not significant. I know you like that phrase. face value.
Yes, I do. You've noticed me using it.
If you want to be proactive about something.
Well, now you're just getting mean.
I know.
Yeah, the point being is that, you know, if I'm the Utilities Commission, I'm going to take this and say there's no significant relationship between high power lines and development of tubers, okay? And that would be accurate. However, if I were a consumer and I saw this is pretty darn close. You know, I'm not going to wait for, you know, for this to go up, my chi-squared to go up 0.2 of a point and say, oh, okay, I'm safe because I'm just 0.2 of a point below it. I'd probably be concerned. Okay, so I'm thinking that practically speaking, as a consumer, this is a concern. So that's my ultimate point is that we use 0.05, I think, as we use that as a strict criterion because we have to use something. But it doesn't mean, I mean, something could be significant and have absolutely no, statistically significant, but have absolutely no importance in the world. This is not statistically significant, it's pretty darn close, but this has a huge importance, a huge impact on us when we buy houses, okay? And this is just this example. So, the lesson, if you will, but the idea that I'd like you to take away from it is that you can't always rely on, you should look further beyond statistical significance and non-significance because it might have either more or less importance than simple statistical significance. I think it has to be evaluated qualitatively beyond that. That's a criterion that we use because we have to use something, and it's traditional in statistics. Okay? Is it late in the day, or is it just me? Everybody looks like they're about ready to fall asleep.
It's okay.
It's late in the day?
Yeah.
I'm hoping it's late in the day and not me.
These Tuesdays have been terrible.
Tuesdays are bad, okay. All right, well, I have lots to look
Every
forward to.
day, actually every day.
Every day.
It's the new Monday.
It's the new Monday, I like that. Okay. All right, any questions on anything with the problems I've talked about so far? I kind of knew what the answer to that was going to be, but I had to ask. Okay, let's go. Let's continue and do a little bit more of our analytical methods, and we'll take a break. So we finished matching. Okay, matching is a way to evaluate confounders, right? To see whether or not your matching strategy actually uncovered a confounder or not. Next thing that we're going to do is stratification. Stratification not only evaluates confounding, it also evaluates effect modification. So it allows us to analytically identify two different potential errors. So we can do this in the design and in the analysis phase of our study, because it's something that is amenable to a lot of data, many data are amenable to. So first thing we do is we stratify based on potential confounders. And there are some examples. And we do separate analyses, either cohort or case control analyses, at each one of the strata. The separate analyses are called stratum-specific estimates for the odds ratio or for the case control or relative risk. And then there is also a summary odds ratio that will adjust for our stratification, and a crude odds ratio. So these are some terms that you kind of have to keep in mind. I'll say the first one is stratum specific. And that's odds ratio or relative risk. Then there is summary odds ratio or relative risk. And there is crude odds ratio or relative risk. And what we'll be doing is comparing the summary and crude odds ratios to determine whether or not we have confounding. So let's talk about the data structure a little bit. Okay. So we have up to n strata. In each one of those strata, we have our standard 2x2 table. Case control, exposed, unexposed. And we'll use the subscript to identify the stratum. So everything in stratum 1 has the subscript 1. Okay, A, B, C, D, and T. Everything in stratum 2 has a subscript 2, all the way down to stratum N. So this is a flow chart of what to do. I'll go through it briefly, but the example is going to make a lot more sense. So what we're talking about now is case control studies specifically. See, look at the title here, case control studies specifically. So that means we'll be talking about an odds ratio. The typical way we analyze case control studies is by the Mantel-Hensel method, right here. Mantel-Hensel. I'm sorry?
This is how I remembered it before.
Okay. So to evaluate confounding effect modification, we have to compute a walled chi-squared, which I will tell you about. That evaluates homogeneity. Okay. If it is homogeneous, then we use the Mantel-Hensel analysis. And then we can calculate the crude and stratum-specific odds ratios. And then we have to calculate the Mantel-Hensel odds ratio and the crude odds ratio and evaluate confounding. If they're similar, there's no confounding. If they're different, there's confounding. The way that we determine difference is rather arbitrary, but it's by a delta percent, by crude minus Mantel-Hensel over Mantel-Hensel, and times 100. And like I said, I'll give you an example. The chi-squared Mantel-Hensel, which we need the Mantel-Hensel odds ratio to calculate, and we evaluate the null and alternative hypotheses. The null is that the exposed and unexposed effects are equal to each stratum. The alternative is that the exposed and unexposed effects are different based on the stratum. Okay? And then we can evaluate effect quantification by looking at the stratum-specific odds ratios. Okay. So then homogeneity among stratas, that means there's no effect modification. Okay? Effect modification confounding can be both or neither present or only one. Okay, these are our formulas. This is our chi-squared walled, and we'll talk about the details of the standard error. The rest of this is fairly self-explanatory. This is Mantel-Hensel. I'm going to assume that everybody has a marginal comfort with summation signs, okay? Because it seems to be the biggest problem is the summation signs in these formulas. So let's talk about this one. Okay. Let's say we have two strata. If we have two strata, then n is equal to 2. Okay, so our odds ratio of Mantel-Hensel would look like, and I'll just write this out symbolically, I equals 1 to 2, AIDI over TI, and summation I equals 1 to 2, these different of BICI over TI. Okay, two different ones. So that means that we have to sum these and then sum these before we do the division. The biggest mistake everyone makes is that they do the division with another division and add the two together. Don't do that. Okay, this is the way we would do this is A1, B1, T1 plus A2, B2, T2. Then Then B1, C1 over T1 plus B2, C2 over T2. You do this addition and this addition, and then the final product, you do the division. Okay? So everybody see what I'm getting at? Don't do this. Oh, I shouldn't even write this up. Okay, don't do that.
Okay, erase it quick.
Yeah, erase it quick before anybody writes it down. Okay? So this is what you want to do. So that's the Mentel-Hensel odds ratio. Now, the reason that I started out with summation signs is because of that beast right there. And let's, just for fun, expand this to 2 strata. We'll do it over in this board. Okay, 2 strata.
Careful.
Thank you.
Occupational safety
that's,
hazard.
that's right. That's always a way to get rid of me. So the first summation is a sub I. So that would be A1 plus A2. That's the first thing you do. That's there. A1 plus A2. And the next is A1 plus B1, A1 plus C1. Subtract and over T1. And since that's inside the summation sign, now we do A2 plus B2 times A2 plus C2 over T2. Okay? And then we square the whole thing. Yeah. Like so. And then you do the denominator, A1 plus B1, C1 plus D1, A1 plus C1,
B1 plus B1
B1 plus D1
over T1 squared
T1,
Times T1
D1 minus 1. Okay. And then for the second stratum, A2 plus B2, C2 plus D2, A2 plus C2, and B2 plus D2. All over T2 squared, T2 minus 1. So that's just for 2 strata. Obviously on the exam I'm going to give you more than 2 strata. Okay. On homework I could, okay. But on the exam, no more than 2 strata. Okay. I didn't say it.
No, you didn't.
Okay.
Now,
Now,
those kicks.
so
Isn't that gonna work?
we need to use this in order to calculate our Mentel-Hensel odds, our confidence interval. Okay, so you have to take your Mentel-Hensel odds ratio, 1 plus or minus the 1 minus alpha over 2, divide that by the square root of your chi-squared. Now, that's an introduction to the formulas. And there is, if you have a heterogeneous, if you come up with something heterogeneous, then you have to do, and this is very unfortunate subscript, but it's what they call it, the standardized odds ratio. Right? You can't calculate chi-squared, you can't calculate confidence interval, and you can only do stratum-specific, compare the stratum-specific potential effect quantification. All right. So, let's take a look at our example. example
Can I ask
is,
a question before we move on?
Sure,
I'm
sure.
sorry.
no, that's fine.
So when you do the chi-squared walled to determine homogeneity, I guess what result of that would tell you whether or not you need to move on into a mantle hensel?
If it tells you, if it tells you that it's homogeneous,
Which
is the null hypothesis. If you
Okay.
can't reject the null
Okay.
hypothesis of homogeneity. Okay. This is our stratified, we have exercise stratified by smoking. And likely the smokers would exercise, but let's say that we haven't found a group that do of some kind, and risk for heart attack. So first thing is our stratum-specific odds ratios. Stratum-specific odds ratio is exactly the same as for a standard odds ratio. It's AD over BC. That's the odds ratio. And you calculate your confidence interval same way. So it looks like, just looking at the stratum-specific odds ratios, that that there's a significant protective effect for exercise among non-smokers. Okay, that I believe. However, among smokers, it appears that protective effect is rendered null. Okay. Again, that makes sense. That's something that I believe. The mental hensel odds ratio, which adjusts for smoking, gives us an overall protective effect. The crude odds ratio is 0.61, similar to the mental hensel odds ratio, which is a valuation for confounding, right? The relationship between crude and mental hensel. Yes?
So would we use the mental hensel odds ratio for the first block of data because it came out to be significant in that it was under 1?
No, the mental hensel is a summary of both together. It's while we are controlling for this potential confounder of smoking behavior, we're seeing whether or not there's a protective effect for exercise. So the mental hensel, like that formula right there shows you, takes both strata into account, as does the crude. Because the crude, what you end up with for the crude odds ratio is collapsing these two together. So it's A1 plus A1 plus A2. So it's 41 plus 86 is our A. B equals 84 plus 68. C is 46 plus 79, and D equals 52 plus 40.
So you're just doing an odds ratio on the transformation.
I'm doing an odds ratio on collapsing the two strata.
Okay, but I guess we find that out the same way that we do the transformation of the matched data case.
Transformation.
Because you're adding, oh no, I'm wrong, I'm wrong.
41 plus
I got
40
you.
these things. Okay.
Thank you.
So this is exposed, this is not exposed, and this is case control. But now what we've done is we've removed the stratification. We don't know who smokes and who doesn't. We're just looking at the effects of exercise. So this is I'll say exercise, don't exercise. How about that? I think that'll be clear. And this will be a case of a heart attack, and this will be no heart attack. Okay? So that would just, all we do is, it's again, the odds ratio is AD over BC. That's that basic odds ratio formula. And we have the chi-squared walled. Chi-squared walled, 1 degree of freedom, 3.84, we cannot reject the null hypothesis. It means that these are homogeneous strata. And we can use the mental hensel analysis. Right. Okay, so this is, again, this is a flow chart, the way we look at that. First thing, chi-squared wall is 0.16, chi-squared is 3.84. It's homogeneous, so that means we can continue with the mental Hensel. So that would be the first thing you'd be interested in, is looking at the chi-squared wall results. The crude and mental Hensel odds ratio are very similar by 3%. So therefore, no confounding due to smoking. Now remember the 3% I got from, okay, is the odds ratio of crude minus odds ratio of mental Hensel over the odds ratio of mental Hensel times 100. And then for us, you can sort of eyeball that, but let's not do that. So that means the crude is 0.61 minus 0.6 over 0.6 times 100, and I apparently found that out to be about 3%. And what we use rather arbitrarily to evaluate that is 10%. If it's greater than 10%, then what we're going to do is assume confounding. So the evaluation criteria is less than 10%. Okay?
Is that, we're always gonna use 10%?
Yes, we'll use 10%. It's a little bit arbitrary, but it's a point that we can use. It's kind of like 0.05. Somewhat arbitrary, but we need to use some criteria, and that's the one we'll use.
And for the, I guess, delta percentage, is that what we're calling that?
Yeah, delta percent. Yeah, that's fine.
We just need to remember that, it's not in our equation sheet.
I will write it on the board. I must have forgotten to put it on.
It's in the notes, but.
Yeah, I'll put it on the board here.
Okay. Thank you.
Just remind me to write it down. Okay, so far so good. It's homogeneous, so we can use mental Hensel. Delta percent is 3%, so that means that our stratification variable is not a confounder. Chi-squared mental Hensel is greater than 3.84, so that means that there's a statistically significant association between exercise and risk for heart attack. Once you have taken smoking behavior into account, it adjusts for smoking behavior. So we have a good association adjusted for our stratification variable. Confidence interval doesn't include 1, that's confirmation. And now let's look at the stratum-specific odds ratios. We've already established there's no confounding, but it looks as if there is some effect modification because you get more protection from exercise if you don't smoke than if you do smoke. Big surprise there. But that's why I like to use something that's intuitive and that makes sense. So that implies an effect modifier. Okay, we have a greater protection from exercise if we don't smoke. Okay. So this is the type of flow chart that I would expect you to go through for each one of these problems, is to first evaluate homogeneity, evaluate confounding, and then evaluate the mental Hensel chi-squared statistic, confirm that statistic with the confidence interval, and then look at the stratum-specific odds ratios and tell me whether or not you believe there's effect modification. Okay. And again, I don't think I put that flow chart on the sheet. I can write up that flow chart because that's not that important to memorize the flow chart. I mean, it makes it easier, but I'll be happy to give that to you during the exam. Okay. Another, let me go through one more stratification example, which is different. Yeah, which is different, and then we'll take a break. This is one where we have risk for nasal cancer, and whether or not there's formaldehyde present. This is in a woodworking shop. Okay? Risk for nasal cancer, whether or not there's a formaldehyde present in your woodworking media. So for instance, in lacquer and other wood treatment materials, whether or not there's formaldehyde in it, and the relative amount of wood dust that's ambient in the air. Okay. So these are our results, our chi-squared wall. This one is actually still homogeneous. I keep going with this, but you can look here and you can see the immediate effect modification, even though at the low wood dust there is no significant association. And on this stratum there's no significant association. It still looks like there's some kind of a potential effect modification going on there. Okay, so let's take a look at our flow chart. First of all, 0.61 is less than 3.84, homogeneous. We do Mantel-Hensel. Crude and Mantel-Hensel is now 20%. It's above our 10% criterion. So it looks like wood dust exposure is a confounder. Okay? The wood dust exposure is the true source, the formaldehyde isn't. It's just present all the time. Okay? So that looks like that would be our confounder. It's a significant association when you adjust for wood dust exposure, and this confirms that. And stratum-specific means, and it shows that we do have a effect modification. Let's go back now. The confounder, once again, remember this would show us that we've got wood dust here. We have nasal cancer. And we have formaldehyde. Nasal cancer and wood dust are a positive association. Formaldehyde and wood dust, at least in this woodworking shop, is a positive association. However, this is this looks like a spurious relationship. It's not the formaldehyde that's coming out of wood dust, according to this analysis. Yeah.
So will it always be, I guess, whatever we're blocking for?
We're stratifying based on potential confounders. That's the idea.
Okay. So the idea is always to do whatever's present or not present or high or low or whatever.
Yes. Yes. Yeah, our stratifying variable. Okay. And voila, I didn't even realize that I did the illustration there. But you get the idea.
Yeah, we appreciate that.
Okay. Problem stratification. This is all case control now. Problem stratification. You get a lot of confounders and you get a lot of strata, you can get very complicated in your analysis. I've just been doing 2 strata here. You can see how complicated these get. So, and the more strata and the more potential confounders you put into your data, the more difficult it is to tease out effect modification and confounding with this method. And you really can't test statistically for confounding other than by this delta percent. That's the only way between the crude and Mantel-Hensel odds ratio. So that's pretty severe limitations if you get complex data. That's why we do logistic regression. Okay, I'm showing you this because of the you get an appreciation for logistic regression where you can toss all these variables together, and in your statistical printout, you get data that will allow you easily to evaluate effect modification and confounding. All right. Now, what we're going to go on to after the break is the same method in a cohort set. Yes, Kurt?
I hate to delay the break here, but
Okay.
are we gonna go back and look at a problem that is not homogeneous and do the whole heterogeneous side of it?
Mhm.
We will.
Yes, we will do that. Yeah, see, that wasn't so much of a delay. So why don't you come back, take 15 minutes, come back at 25 after, and then we'll go from there.